Good afternoon, everyone. Thank you for joining us as we discuss how regulations are changing everything and how Passive House helps mitigate growing risks. I'm presenting today with Dylan and James. I'm Ryan Cattley, Senior Project Engineer at Jarrows, Bound and Bowles.
I'm Dylan Martello, a senior building systems consultant with Stephen Winter Associates.
I'm Jimmy Lynn, associate partner with JBMB, focusing on HVAC design. So today we're going to discuss the recent legislation, carbon reduction legislation passed by New York City and New York State, namely Local Law 97, and how these pieces of legislation are pushing for building electrification. And very specifically and appropriate for us here today is how some of the tried and true passive house design principles can help building owners and design professionals like us to design buildings that are towards Local Law 97 compliance, as well as feeding back the other way where we have some of the prevailing design strategies for Local Law 97 feeding back to the passive house community and arming them with some additional ideas in the arsenal for designing passive house buildings. So Local Law 97 here in New York City, it's essentially a law that has been passed in May of 2019 that effectively puts caps on carbon emissions for buildings. It takes effect in January of 2024 with a ratcheting down or lowering of the carbon emissions limit every 5 years. The consequence to building owners is that if you're outside of the limits, you're paying a fine for every ton of CO2 that's emitted. So it's a fine for the building, not a tax. As far as we understand, can't be passed along to tenants. So building owners are really incentivized here. So carbon coefficients here, basically the way this works is building owners are required to submit their utility usage data to the state, and each type of utility is assigned a carbon coefficient. So whether you're using electricity, fuel oil, natural gas, or district steam like we have here in New York City via Con Ed, each one of those types of utilities is assigned a carbon coefficient. And interestingly here, you'll see that we're talking about building electrification, but currently grid provided electricity has the highest carbon coefficient of all of the utilities at this time. But more on that in a minute. So how do you calculate what the carbon emissions limit is for a building? It's pretty straightforward. The limits are set by the DOB occupancy type. So the local law has specific numbers for each type of occupancy, whether it's business. In this case, we have an example of a mixed-use building. This question comes up quite a bit. How do we calculate when we have different occupancies? It's quite simple. It's just prorated based on the gross square footage of the various occupancy types. And the carbon limit for the building as a whole is just the aggregate of all of the parts. And here we have a case study, again, illustrating the why building owners are incentivized to take action to reduce the energy usage in a building. So here is a building, 200,000 square foot, business occupancy, so commercial office building, built not super old, and the type of building, it's not an all glass building either, so it's not one of those super high rise, all glass buildings, but it's got a higher percentage of glass. The actual emissions here is a little over 3,300 tons of CO2. And you'll see here that the carbon emission limits under the 2024 limits there were actually below those limits, which we'll see as the case for most existing buildings. So you're paying zero fines from 2024 to 2029 if you did nothing with the building. Now 2030 is a whole other story where the limits get ratcheted down, and now the limit is a little over 2,500 tons of CO2, whereas we're actually emitting a little over 3,300 tons, multiplied by the $268 a square foot penalty. Building owners would be paying a little over $220,000 per year in fines if they did nothing to upgrade the building. In 2035, although the carbon emissions limits have not been published or established yet, using a little bit of logic and the same percentage of reduction between the first two periods and applying it to this third limit, the building would be paying over $550,000 in fines per year. So, in that first, or I should say the second tranche here in 2030, the building is essentially paying a little bit over $1.10 a square foot in fines. So, you can think about this, and building owners, would they rather pay this money to the government, or would they rather spend this money to upgrade their systems and potentially building an envelope? So it's a very compelling case to move and actually make the changes. New York State also passed legislation here that is in support of the local law 97 carbon reduction. With all of the different elements of that piece of legislation there, the most important or most pertinent to us are the ones here in green. Basically, by 2030, the state has committed to having a 70% renewable electric grid, and by 2040, it's 100% renewable. So back again to our discussion about carbon coefficients for the various types of utilities, right? Electricity is the only one that has the potential for and a commitment from the state of New York to be 100% renewable, therefore dropping the carbon coefficient down to zero. So again, another really compelling reason to electrify your building. We're going to pass this to Dylan to talk a little bit more about building electrification.
All right, thanks, Jimmy. And as Jimmy mentioned, I'm going to kind of reiterate this point of the importance of building electrification and how it relates not just to what we as building designers and building developers are considering as it relates to reducing the carbon footprint of buildings, but also how this relates specifically to passive house design. And I want to actually touch on passive house certification as well, partly because there is very recently, over the last 5 or so years, there's been a big push in, I think, specifically the New York City market, but now we're seeing in other markets across the US and North America for projects to actually achieve certification. And there's specific incentives and specific other aspects of a project's development that are actually tied to specifically certification, and there are benefits to that. So this is going to be a fairly technical portion of the presentation where we do get into specifics about how this all relates, how building electrification all relates to getting your project passive house certified. With New York State having these goals in place and these mandates in place to really push for a decarbonization of our electrical grid, what happens is this grid coefficient, or the associated carbon with the electricity use in our building, will go down as our grid gets decarbonized. And that really paves the way for electric systems in our buildings, like electric heat pump technology, to be very efficient, not from just an energy standpoint, but from a carbon standpoint. And the important thing to remember here is that the carbon coefficient of electricity, while that is expected to drop over the next 20 to 30 years as we decarbonize our grid infrastructure, the alternative fuel types like steam, gas, fuel oil will not. And that's really important to remember that, we're building buildings that will last for 80 to 100 plus years, hopefully. That's what we're doing when we're designing a passive house building. We're making buildings to last. So the decisions that we make today will really translate to decisions that we may not have to make in 20 or 30 years. Diving into specifically passive house and how it relates to certification, and particularly with respect to electrification of our buildings, I want to talk about one of the key energy thresholds for passive house. And this is what we call our primary energy. Our PE is sometimes what it's abbreviated to. And for those that aren't familiar, this is, I think, a term that is more of a European context term. It's not necessarily referred to in the North American climate as much. However, it is, the terminology for passive house. And really, when we talk about primary energy, what we are referring to is all of the energy use in the building summed up. And the other component to this is we're not looking at just the energy use at the site. We're looking at what we call source energy, which accounts for any additional energy that's being used by the power plant to account for any inefficiencies at the power generation facility or any transmission losses through the grid infrastructure. And that's really important to understand, because what happens here is like we have a grid coefficient for carbon, for electricity and the various fuel types, we also have what we call a site to source factor, or site to source coefficient. So essentially what this means is for every 1 unit of electricity used on site, you will have a certain amount of electricity or energy consumed at the actual power generation facility. And I'll talk about those factors in a second. But when we look at primary energy, it's important to note that under the passive house standard, the PHI standard, there are 2 pathways that a project can go down to show compliance with this threshold. One is called the primary energy, or PE, which you can think of this as the building under today's grid infrastructure. We have a lot of coal-fired power plants. We have a significant amount of natural gas-fired power plants. We have peaker plants. We have some cogen, some nuclear, some renewable scattered in there as well. So think of primary energy as that kind of source energy impact of our building under today's grid. This threshold is a fixed threshold. It's project specific, which is why there is a range. Typically ranges anywhere between 38 and 45 kBTU per square foot per year. It depends on things like project density, what the use type is, if it's a multifamily or an office building that can impact this. But generally, this is the range, and that it is one fixed number for a project that you need to show compliance with your energy model, and you need to show that the total building source energy, primary energy demand specifically, is less than that fixed threshold. Under the primary energy standard, or the primary energy pathway, the site to source coefficient or factor for electricity is 2.6. So for every 1 unit of energy used at the site, that's electricity use, there's 2.6 units of energy when we look at it on a source basis. So there's a big kind of jump there from our site to source when we look at electricity. And this is similar to, as Jimmy mentioned, how it relates to the carbon coefficient for electricity under Local Law 97 is also much greater than some of our alternative fuel types, which, as you can see here, natural gas has a site to source factor of 1.1. So there's a much less of a source impact there when we look at natural gas fuel type in our building. Now, the alternative path here is what is referred to as the primary energy renewables, or PER is commonly what it's referred to or abbreviated as. This is got a little bit more of a complicated things going on behind the scenes in terms of how the PER is actually calculated. But I like to boil this down into simple terms, is just think of this as the building's source energy demand in a decarbonized or green grid infrastructure. which we know we're not at yet or not at today. However, as we were alluding to before, there are mandates and goals in place to push for decarbonization of our grid infrastructure. And this is kind of the path we're trending towards over the next 20 to 30 years, hopefully, with respect to our energy grid infrastructure being decarbonized and being this kind of green grid infrastructure. So the primary energy renewables, or PER demand for your building, is essentially the source energy demand of your building under this context. Electricity site to source factor, we kind of look at this in an apples to apples comparison. Under a decarbonized grid infrastructure, there is far more distributed renewable energy generation. There's ideally some grid level storage and potentially changes to our transmission infrastructure, but that's a little bit out of my expertise. But the idea is that our grid infrastructure will be a lot more efficient as well in a decarbonized grid economy. So the electricity site to source factor now, instead of being 2.6 as it was in the PE path, it's now anywhere from 1.1 to 1.3. So it's much less of an impact. And the reason there's a range there is it actually depends on end use and time of day when your electricity demand actually occurs. That's really, really important, and keep that in mind. The natural gas site to source factor, however, when we look at the PER based path, goes up from 1.1 to 1.75. There's a much more of an impact on a source energy demand basis for using a natural gas fuel type. And the reason for this is a little bit, it's very technical, but natural gas is expected to be, the availability of natural gas is expected to be far less in the future. Gas infrastructure will not be as prevalent in 20 to 30 years, as we're already starting to see in New York City in particular, and Massachusetts is another area where there's really a push at the utility level away from natural gas, new natural gas infrastructure. When we look at primary energy renewables, PER, in terms of showing compliance, it's a little different than PE because this is essentially judged more on a curve type basis. I've tried to explain this to clients and other building designers even, and have admittedly struggled to explain this. So I'll be honest with you. I've tried to really boil this down in a simplified manner. And this graph tells the story. So the red X is what I'm going to say is our current building that's being modeled in our energy model. And the goal simply is to get the red X within the orange shaded region. That means you are complying with the PHI-PER threshold. Now, you may ask, okay, well, how does this red X move on this graph? So in order for you to go left on this graph, if we needed to go left on this graph to get into that shaded region, essentially what you need to do is reduce your building's energy consumption. So if it's cutting your common area lighting energy use by 10%, that'll get you to go 10% on the left there, just about. Now to go up or down on this graph, it's related to renewable energy produced on site. So if you wanted to go up on this graph, you would conceivably add renewable energy production, or if it's an on-site PV system, you would add some additional PV capacity to get within that shaded region. But that's really the goal, and that's how this is judged. So when we talk about how this all relates to building electrification, because this is ultimately what we're discussing here, the decision on whether or not a building will be all electric and if they want to be certified to the PHI standard will really have an impact on which path is chosen here. The PE path, because of that site to source factor being 2.6, when you compare it to natural gas being 1.1, essentially all electric buildings can in effect be penalized under the PE path. So what happens is any project that's all electric, it makes much more sense to go under the PER pathway because fossil fuel use is actually penalized a little bit more than electricity use. So keep that in mind. This is really important. I'm saying this for a couple of reasons, not just related to certification, as I'll get into in a second. There's other aspects of things outside of pH certification that are tied to this exact point here. But before we get into that, I want to quickly just show you a case study to kind of hit this home. So what we're looking at here, it's an example project in New York City. It's an 18-story building, about 300,000 gross square feet, and 311 unit affordable multifamily development. We're assuming a 135 kilowatt PV system on the roof. And we looked at two separate scenarios for this building. The first scenario in green is the all electric scenario, which assumes heat pumps for heating and cooling, as well as domestic hot water. The second scenario we looked at, which is in red, is again, heat pumps for heating and cooling. However, we have a gas boiler plant for domestic hot water. Now, the graph on the left is our primary energy, and we're showing our red X or green X for the different building scenarios. And as you can see, under the PE path, the primary energy path, the gas domestic hot water version of this building is actually performing better and is falling within that compliance threshold. The all electric building, even with heat pumps for domestic hot water, and now we're assuming a COP of about 2.0 on the heat pumps for domestic hot water, which we know could get a little bit better than that. But under that conservative assumption, the all electric building is actually not complying with the PE threshold and is worse than the gas boiler plant scenario. So what we look at now on the right is how this all changes under the PER path, or primary energy renewables path. Now, as you can see, our all electric building is much better than the gas domestic hot water version of this building. We're still right along that compliance threshold, but we are passing. And we really could never get there with gas domestic hot water. No matter how much PV we produced, we're not going to be able to fall within that orange shaded region. So this is really important to keep in mind and remember, as whether or not you're a building designer or a building developer and considering pH certification for your project and are grappling with the idea of whether or not to go all electric. This is one thing that's really important for particularly the Passive House consultants that are involved on that project. As I mentioned before, this is something that we don't deal with just as it relates to Passive House certification, but there are other things that can be tied to this. And one example of this is an incentive program. I'm going to use the NYSERDA new construction program as an example here, where incentives are tied to certification and specific thresholds are set based on how well you perform, not just at a certified level, but going above and beyond a certified level. And really what I want to drive home here is that programs need to essentially be able to accommodate this PER method or kind of acknowledge that this is the path for all electric buildings in terms of Passive House certification. And if there are any aspects of the program tied to a PE or PER number, that the PER is accounted for in that program. And the reason why I think this is really important to mention now is, up until probably the middle of last year, even, the projects that our firm has been working on, the Passive House projects that we've been working on under the PHI standard, only one of about 20 or so actually certified to the PER threshold. And that one project was a very unique scenario. It was halfway across the world in Sri Lanka and all electric, and not necessarily representative of what the building stock in the North American climate is, which, as I mentioned, up till about the middle of last year, 95% or so of our projects were going through the PE path. However, we are now in middle of 2020. Time is really flying here. And, we have at least about 12, potentially more new projects in the pipeline, and all of which are considering going all electric and actually have as a basis of design an all electric building, which means, as I mentioned before, they're going with the PER path. So we have a lot of new projects coming up in the pipeline that, are in early design, but next year, they'll really be kind of, cranking away in design or even in construction. And they are going all electric and will be through the PER path. So, this is the North American Passive House Network Conference, and we all have hopefully some familiarity with the Passive House concepts, but we do want to kind of quickly reiterate them, just for anyone that may not be up to speed. So we're showing here just a simple diagram and some 8 main design concepts: building orientation and site selection and shading being the first 2 here, are obviously very important, especially in the New York City climate, where you have a lot of neighboring buildings and a lot of tall buildings. Those are very important. High efficiency heating, cooling systems, as well as high efficiency energy recovery ventilation, in particular balanced ventilation is critical. Has numerous benefits, not just from an energy standpoint, but also from an indoor air quality and health standpoint. A continuous air barrier that achieves an air tightness level of 0.6 air changes per hour at 50 pascals or better, substantially more airtight than typical construction. The envelope systems is obviously crucial here. So high performance continuous insulation and a great level of detail on mitigating thermal bridges in our building and analyzing thermal bridges and dealing with them if they do occur. Of course, triple pane windows as well. And with triple pane windows, the benefits there are not just from an energy perspective, but also from a comfort perspective as well. It's a really major tenet of Passive House design. And lastly, efficient appliances and plug load management, as well as efficient lighting energy in these buildings. It's another major aspect of not just all buildings, but particularly with some of these larger scale buildings that we're discussing in this presentation. So with that, I'm going to turn it over to Ryan to talk about how a typical building who may not be considering Passive House certification, but are looking at just complying with Local Law 97, how that relates to these design principles and what of these 8 they would probably be choosing.
All right, thank you, Dylan. So even though there are all these great energy saving concepts that we employ in Passive House design, we are seeing that buildings aiming for no fines under Local Law 97 are typically only integrating just a few of these measures. These being high efficiency energy recovery ventilation, triple pane windows, and high efficiency heating and cooling systems in some form. Although it's important to note that even though only a few of these measures are being implemented in Local Law 97 compliant buildings, this legislation has started the conversation to some extent with various stakeholders talking about how Passive House could potentially help them in their quest for Local Law 97 compliance, or even just to implement some of those energy efficiency measures. And really, the reality is that more buildings will need to incorporate more energy conservation measures because the energy codes, not just in New York State and New York City, but across the country, they are getting more stringent. So, for example, air tightness has been a part of the energy code in recent iterations. It's certainly becoming a more substantial part with the latest code iteration. And it seems that thermal bridging will also make its way into the energy code in the near future. So even though there's only a few measures here that are really being implemented today in a building that is aiming for no fines under Local Law 97, there are still, it seems that many more Passive House concepts may be implemented in the future. So this is a case study of a fully electric building that is aiming to have no fines under Local Law 97. This is a 700,000 square foot occupancy Class B office building that is using those energy conservation measures from the previous slide. The triple pane windows, high efficiency heating and cooling systems that in this case are fully electric for heating and cooling. There's no gas in the building, and high efficiency energy recovery ventilation. So we would typically expect to see a code minimum, an energy code minimum building to have an EUI in the 70 to 75 range with the current codes. The building in this case study with implementing these three energy conservation measures ended up in the 42 to 52 range, meaning around a 30 to 44, 45% improvement above code just from these three measures. So this is one of my favorite slides in the presentation. One of the great things about Passive House is that it is a performance-based standard. And this is measured in kBTU per square foot per year, or EUI. So since Local Law 97 is also based on building site EUI, that makes it very easy for us to directly compare and have an apples to apples comparison of the Passive House standard and how that relates to Local Law 97 EUI and subsequent carbon emission and carbon caps. So when Local Law 97 was first passed, the industry was panicking to some extent for fear of having to pay substantial fines, as Jimmy mentioned earlier and demonstrated earlier in that case study, and also not necessarily knowing how to construct a code compliant building that will alleviate these fines and some of these fears. However, from this chart, Passive House is a pretty clear answer to this question. Even if some are hesitant to go the Passive House route, here is a method of constructing a building that will comply in all likelihood with Local Law 97 in the future. And it's something that we've been doing as Passive House practitioners for 20 plus years. So here in this slide, we have overlaid the case study that we were just discussing with the typical code minimum office building and the Local Law 97 driven all electric building. So this purple line that we've overlaid is as I mentioned, a typical code minimum office building with the EUI in the 70 to 75 range. And this building in particular is not facing fines under the 2024 carbon limits, but it will be facing fines under the 2030 carbon limits. The other line that's overlaid here in blue is the all-electric Local Law 97 driven building that will not face fines until potentially 2035. So an important takeaway from this slide, in particular, the Local Law 97 driven all electric office building shown in blue here, is that it's important to remember that the New York State law, if the New York State law is successful and there is a 70% renewable electricity grid in 2030 and a 100% renewable grid by 2040, the carbon coefficient for electricity and therefore carbon produced in an all-electric building, that blue line, will drop to zero in theory. So some of what we're seeing is a two-pronged approach to compliance with Local Law 97 with short-term efficiency gains to make sure that there's, to try and avoid fines under the 2024 or the 2030 limits. And then creating designing a fully electrified building. That way, when the grid becomes more increasingly renewable, the buildings are less and less likely to face fines as the carbon coefficient for electricity will, in theory, drop to zero with a fully electrical or fully renewable grid. So now we're going to shift gears just a little bit and discuss some of the design changes and innovations that have resulted from the New York State carbon legislation. So just to take a step back for a moment and really put this into context, Local Law 97 has had a massive impact in New York City with, again, more than 50,000 buildings being affected. While the 2024 limits are aimed at and will affect about 20%, the worst 20% performing buildings, in 2030, it will affect about 80% of all of these buildings in New York that are greater than 25,000 square feet. So there's a really tremendous push for all of these buildings to meet compliance, particularly in 2030, with 80% of all buildings over 25,000 square feet being affected. So there has been some industry pushback, some comments that maybe this is a phase, maybe this law will go away, or maybe this law will change as administrations change. But we really have not seen any indications that that will be the case. The law passed with overwhelming support in New York City Council of 45-2. So let's talk about approaches to efficiency in passive house as compared to Local Law 97 design buildings. On the left side here is what many of us would consider to be a typical or traditional passive house type building and infrastructure with variable refrigerant systems, VRF for heating and cooling, and natural gas fired domestic hot water. In the middle are the passive house concepts from the previous case study that we've seen used in buildings aiming to achieve Local Law 97 compliance, being the high efficiency heating and cooling systems of some kind, triple pane windows, and dedicated outdoor air systems with high efficiency energy recovery. And then on the right side are the systems that we are typically seeing implemented in new buildings designed to be Local Law 97 compliant. So these are hydronic heating and cooling systems. We're using air source heat pumps for the space heating, high efficiency cooling systems, just a more highly efficient version of a traditional chilled water or chiller plant system, and either air or water source heat pumps for domestic hot water. So why are we using these systems to try and comply with Local Law 97? So this ties back into higher efficiency in the short term to stay under carbon limitations in the near future with the 2024 limitation and the decrease in carbon cap in 2030. And then this also allows us to create a fully electrified building for the long term in anticipation that an all electric building will produce no carbon with a fully renewable grid. So on this slide in the left is what you might find in a typical office building with natural gas fired boilers for space heating and for domestic hot water. So to electrify this boiler plant, we are using air source heat pumps for heating and then either air or water source heat pumps for domestic hot water. Now there are some limitations with transitioning from a natural gas fired boiler plant to air source or air or water source heat pumps for heating and domestic hot water. Air source heat pump space requirements can easily be on the order of magnitude of 10 times the space required as compared to a traditional gas-fired boiler plant. Air source heat pumps, at least with today's technology, cannot create as hot or as high of temperature as water as a traditional gas boiler plant. And also the day one utility costs, particularly in this region, the New York City and New York State region, will be much higher compared to gas. Natural gas is cheap per BTU compared to electric kilowatt hour costs. So there are some limitations. While hydronic heat pumps are relatively new, the technology will continue to improve. A good example here is cell phones, where once upon a time there used to be this massive device with this brick of a battery attached to it. And now we essentially have a computer in our pockets. So we do expect that as more and more manufacturers start to respond to Local Law 97, we will start to see a reduction in the size and the space requirements for air source heat pumps, an increase in efficiency, and an increase in the water temperature that we can deliver with these systems. It's also important to note that there is no cooling shown on this slide. With hydronic cooling, we have an electric drive chiller plant with the chillers and a cooling tower, both being already fully electric. So there's less of a dramatic change here. We're just using a higher efficiency chiller system. So how do these concepts and these equipment changes relate to Passive House, and is there anything Passive House can learn here? So this is a case study, occupancy group B office, around 576,000 square feet. And this is a case study that was modeled in both PHPP and Energy Plus. So Energy Plus is an hourly 8760 dynamic energy modeling software that's widely used for things like code compliance with the DOB or for lead energy modeling. So in our base case here, this is the previously discussed sort of conventional passive house building with a VRF system for heating and cooling, gas boilers for domestic hot water, and energy recovery ventilation. In our hydronic case, we substituted in air source heat pumps for space heating, high efficiency magnetic bearing chillers for cooling, and water source heat pumps for the domestic hot water. And we also have the same high efficiency energy recovery ventilation. So the system configuration on the right here is representing the hydronic case in this case study. And it also gives us, with the substitution of the boiler plant with air and water source heat pumps for space heating and for domestic hot water, it gives us an additional opportunity for heat recovery from our chiller plant. So typically a water-cooled chiller will create chilled water for cooling the building, and then it will reject heat to the outdoors through the cooling tower. However, in this case, because our air source heat pumps are operating at a lower hot water temperature, we can actually use that heat rejection, or at least some of that heat rejection from our chillers, to help heat our building hot water loop, to help meet our building space heating demand. So whenever there is simultaneous building heating and cooling demand, which in an office building, you will generally always have a year-round cooling demand due to the high internal loads typical to an office building. So in those instances of simultaneous building heating and cooling, we can recover that rejected heat from the chillers. And instead of just rejecting that heat through our cooling tower out of the building, we can use it to actually help heat our building, which means that the air source heat pumps don't have to run as often or work as hard. So these are the results from this case study. So the PHPP model is shown in blue here. Energy Plus model is shown in green. The baseline case, as I'll call it, is the traditional passive house or conventional passive house multifamily building, or the systems you might expect to see in that type of building, with the variable refrigerant flow for heating and cooling, the gas domestic hot water, as modeled in the passive house planning package, PHPP. And then the Energy Plus model for this base case was within 1%. So the middle case here is substituting the VRF and gas domestic hot water system for our high efficiency electrified hydronic systems. So the next case we'll focus on here in the middle does not take into account any of this heat recovery from the chillers. So we're assuming that we're not recovering any heat, and effectively there's no simultaneous heating and cooling in the building. Whenever we are running our chillers, we're rejecting that heat directly to the outdoors via the cooling towers. So this case is important because while this case study does focus on a passive house quality envelope in a office building, this case in the middle is more aligned with something you may see in a residential building, a multifamily residential building, where you don't have that simultaneous heating and cooling, because in the wintertime, there's very little internal heat gain, typically, that you would find in a residential building, at least compared to an office building. And finally, the last case here is taking into account the heat recovery from the chillers. So we're using the chiller heat rejection to help heat the building in the shoulder seasons and in the wintertime. So what are the key takeaways from these results? So first, all these results are very close together, very, very similar. Almost within the noise of a typical energy model. So this points to the fact that VRF is not necessarily the only answer for Passive House. While it makes sense for many projects, the push to comply with Local Law 97 has shown us another potential option for Passive House projects. And finally, Passive House could have a lot to learn from legislation-driven solutions in the future. Local Law 97 was only passed about a year ago, year and 2 months, April 2019. So it'll be really interesting to see how legislation continues to shape design and innovation in year 2 of Local Law 97, or 5 years from now, or over the next 10 years and beyond. So the Passive House community needs to continue to pay attention to parallel paths to building efficiency and how those are influencing and shaping design. It's an exciting time for high performance buildings.
So many of you are probably wondering, all of this COVID-19, pandemic talk, and the responses that building owners and design professionals like us are kind of leaning towards and thinking about. How does that play with what we've just talked about? Carbon reduction, energy reduction. And how do the two kind of work with each other, or do they? So we'd like to just talk a little bit about that here. Ryan, you want to chime in?
So it's really interesting how Passive House can play into this, at least in terms of an airtightness. If we start to think about what envelope airtightness means, or lack thereof means, in a practical sense, if you have an envelope that's not constructed to Passive House standards, that's not relatively airtight, you will have significantly more infiltration of unfiltered New York City air, which many of us know is not necessarily the greatest experience, right? So contrasting this with Passive House, where we have balanced, controlled ventilation that's also filtered, and we're controlling our air volume in the building by having an airtight enclosure. I think this, Passive House has an advantage in some ways because we have this airtightness in place.
Yeah, and Ryan, I think I would add to your points, which were great, that designing to the Passive House standard and taking it a step further by certifying to the Passive House standard really ensures that your building is built to the highest quality possible and built in a way that is true to the design and achieves the level of performance that we've designed to. And I think remembering that, specifically, not just as it relates to air tightness, but also how your ventilation system is commissioned and, how you deal with things like duct leakage, which could be a major source of, cross-contamination of, from pollutants from one apartment to another. Dealing with issues like that is really addressed in a Passive House design. So I think remembering that and understanding that there is a really great synergy there between designing high quality buildings, designing buildings in a post-COVID world, and designing your building to the Passive House standard is really crucial to understand and consider for your projects moving forward.
And, as far as New York City is concerned, my firm's involvement on the code committees, various code committees, we know that the city has been asked a specific pointed question of, Is there any relief? Is there any consideration given due to the pandemic, and what buildings have to do to make buildings safe? And quite honestly, the answer from the DOB has been no. Local Law 97 is still Local Law 97. It will still come into effect. Potentially there may be a little bit of leeway, but as far as we know, there's no planned changes to any of it. So there you go. Design better buildings. Design more efficient buildings.
I mean, Dylan, you brought up an interesting point, right? On the construction side, given that you're a little bit more involved in the, with the contractors in the construction side, can you give us a little bit of an idea of, what that's like and what a contractor and what they have to go through in terms of quality control to make sure that a building's actually constructed as designed, right? Because we can design a great building on paper, but what happens in the field happens in the field a lot of the times.
Yeah, that's a great question, Ryan, and one we deal with a lot on our projects at our firm. And I think that one of the first steps is just educating the contractor on what it means to design and build to a pass-fail standard. There's a lot of mythologies, or there's some myths that are out there with what it means to design and build to a pass-fail standard. And really there's a big unknown factor that can happen with a contractor that is not familiar with how to build or design a pass-fail building. So the first step is just educating them on what it means, what it actually means to them. And really, all of our buildings, the first thing that always gets asked about is, oh, well, the air tightness is extremely tough to get. We don't know how we're going to get there. And we're going to increase our fees by 20% because we're not sure what additional things we need to do to get that level of air tightness. And we have to step in and say, look, you're already installing an air barrier system for your building. You have to do that by code. There's really not a whole lot of additional steps you need, additional materials that you need to get there. It just requires a bit more attention to detail and QA/QC procedures to make sure that the building is built with a continuous, robust air barrier system, but you're not really introducing new materials. So that educational aspect is really key. And then we step in to really provide assistance on the QA/QC procedures, both in design and construction. So we develop an air barrier set where we quite literally draw a red line around the whole building and circle every little detail that needs to be coordinated with the contractor. And we discuss that in design. So that way, if there are any constructability issues, they're addressed before the building is actually in construction. We also develop inspection checklists that are for both unique conditions and typical conditions, and how the typical inspections that we do overlap with what's already required for code inspections. We all have to look at insulation. It's just, can we find a way to overlap our inspections and deal with what's required for pass-fail verification under what's already being done with the project. And that's a really important step. And then in construction, we have various QA/QC procedures like window mock-up air tightness testing. We do a guarded blower door test where we can actually pressure test one individual floor. We go around with smoke with the contractor, theatrical smoke that is, that will show where air leaks actually occur. And it's really, you can put a report out that says, hey, your window is leaky and you need to fix it. But what we found is a lot more effective is to actually have the contractor on site, and they see the smoke going out the window and they're like, oh, okay, yeah, now I get it. This is airtight. This isn't airtight. We need to fix this. So it's really about, integrating with the project as much as we can. And one other question that gets brought up a lot is, will this impact project schedule? And what we found is that no, it does not absolutely impact project schedule as long as we have this integrated QA/QC process, throughout design and construction. And what really helps that is to get the contractor on board as early as you can in design. Even if it's construction documents or as early as DD or CD, that is a very important, DD or SD. That's a very important part of making sure that the contractor is doing what they need to do in construction to make sure that we achieve the passive house level. So it's a great question, one we get asked a lot, and I think it's always important to bring up. So I think, thank you, everyone.
I think so. Bringing this back a little bit to the COVID or the post-COVID discussion, right? Two key takeaways is that we're not anticipating any relief in energy standards, energy code standards, due to the pandemic, or perhaps on a limited scale in specific cases. But by and large, we're not anticipating any broad scale relief due to the pandemic. And I think, as Dylan demonstrated, there's, passive house really does have a leg up in some regards with quality control and air filtration, balanced ventilation, and air tightness.
Thank you, Ryan. And as everybody can see, the legislation is really driving innovation at this point. Local Law 97, was essentially passed without consideration of, or very little consideration to what the commercially available technology is at the time or was at the time. And even in the short year and change that the legislation has been out there, we're already seeing, manufacturers working with companies like us to drive new products in order to accommodate, kind of our climates up here in the Northeast, and to drive efficiency of those pieces of equipment, and also to start to scale down the size of some of the product offerings that they have. And right, it's a really exciting time in that, as Ryan said, right, there's kind of the interoperability of trying to true passive house design principles that can be applied in Local Law 97, and all of these new technologies and design concepts that we have coming out of Local Law 97 that can be fed again back to the passive house community here. And I think, there's a lot of synergies between the two, and there's going to be lots and lots of opportunities to draw from each other and be successful in creating high-performing buildings in the future. So thank you, guys.